we can start. Thank you very much. Good afternoon to everybody. Thank you for being here. I'm going to hand over to Sandra. And Maarten, welcome. Thank you for being here.
Great. We'll just give it a few more minutes for everyone to join in. Okay, sorry for that, everyone. Thanks for your patience, for those who did hang in there. I'm going to hand over to Maarten. He's going to take us through today's first session, and then I'll take over from him about halfway through and take you through a few other hands-on things with R. So thanks, everyone, for being here.
Good afternoon, everyone. Can you hear me? Okay. Welcome to this fourth and last lecture, where we will give some guidelines on how to use open science. This will by far be an extensive overview of everything that you can do, but we will give you a few hints of how you can improve your way of working into open science. We received a couple of questions on the previous lectures. So the recording of the previous lectures will come online. And so you can see the website here on the screen where you can find those lectures there. So the recordings are on YouTube, and also our slides will be made available. Moreover, it's just, again, a warm welcome to contact us if you want more information. So definitely don't hesitate to do that. What is open science? We touched upon this topic in the first lecture mainly, and this is consisting of the FAIR principles, which we covered, but also publishing in open data repositories. And it's actually mainly this publishing into open data repositories, the data sharing, and data sharing can be looked at very broad now. We are not only looking at data, but also on software and coding. How can we use these open repositories to share our work? And a few examples are already here available on the screen. GitHub, Zenodo, I will touch upon them later on in the lecture. One of the first things, and that's another thing I forgot to mention during my lecture, the first practical lecture that we presented, was how do we find this data? And moreover, we were looking at how to find the quarter-degree ridsels of South Africa that I was using in my demonstration. And Zenodo is here a good example, and I will stop sharing the slides and go into the practical demonstration of this. So here you can see the Zenodo. Zenodo is a repository hosted by CERN, the Physics Institute in Geneva, where part of their infrastructure that they use for sharing their massive amounts of data is shared with other disciplines. So we can use Zenodo as a repository for our data. And the good thing about Zenodo is that they are already implementing the FAIR principles. For example, if you see here, this is the quarter-degree ridsel of South Africa that I used during my demo. It has already a version, so it's versioned, and it has a digital object identifier, a DOI, attached to it. Moreover, it contains a lot of metadata about this data set that people can search for. For example, there are a few keywords that you can look for, how you can look for this data set, what kind of resource type it is, the publisher, and so on, and how you have to cite this data set. So basically, all the information that you need about this data set can be stored within this Zenodo repository. It even has the license that you can that you know what you can do with this data. The useful thing about having keywords in this Zenodo repository is that you can search for them. So for example, if I want the quarter degree grid cells of someone from another country, I can search for that, and I will get some. I'm now within in the community, but that doesn't. I will get to the point of community itself. You will get all the quarter degree grid cells of the countries that are already created, and if someone added this to Zenodo, you should be able to find them according to these keywords. Zenodo is a huge database, so sometimes it becomes a bit difficult to find what you want, and therefore many of the data sets are gathered into communities. So for example, this data set is in the community quarter degree grid cells, which actually is aggregating all the different data sets that are useful when you are looking for quarter degree grid cells. There are many other communities on Zenodo, and you can search for other communities. For example, I can search for the community of our garden, and then you will see that there is a community, Master Botanic Garden, our institute, which is actually gathering all the output of one single institution, one single project. It can be organized in many different ways, but it's very convenient when you know more or less what you are looking for. So this is somehow touching upon a question that was raised. So where do you get this quarter degree grid cells? You go to these open repositories and you search for them. And Zenodo is really a very good start when you are looking for specific resources. But not only when you're looking for resources, it's also good when you want to publish your data yourself. And let's go to the main page of Zenodo here. What we can do is, with this plus sign, we can add uploads. So for example, I can start a new upload. And what you can do here is simply a very easy interface. You can drag and drop the files that you want to share. You can assign a DOI to it, a title. You can give all the metadata that you want for this data set and explain how people should use your data set. So this is very convenient. This is an open repository, so anyone can do this. So it's very highly encouraged when you have any data that you collected or data results from your research to upload them to Zenodo. And we will get to this in the next step. You can even publish your software code here, because Zenodo itself is, they have an engagement to provide this repository as on the long term. So if you really want to preserve your data or software on the long term, Zenodo is really a good place to go to. Zenodo even connects to all your other accounts, and that's quite kind of important. Whenever you should create an account on Zenodo, but you can, if you go to your own profile, connect, or if you look here, you have a section linked accounts. You can connect your accounts to Zenodo, which will make the data flow from wherever you want to publish to Zenodo much easier. And you see here that both my GitHub account and my ORCID, my identifier, are linked to Zenodo. So whenever I publish something to Zenodo, it's immediately a record that can be linked. We can take a little side step here. I also want everyone to encourage to make sure that you have your own unique identifier available for the research community. Why? This is because this is a very good way for making sure that people can find you and that they attach your outputs to the correct person. Because names of people are not unique, but your org ID is a unique thing. So if you don't, for the audience that's now listening, if you do not have an ID yet, please go and create it so that you can easily link all the works and data sets that you have published to your name. So for example, here is my own one. You can see that all the things that you ever published, even if that's on a Zenodo repository, will be linked to your name so that people can also give credit to what you have done. Okay, that was a little side step, but definitely for people that don't have an org ID yet, to think of creating one. Okay. How now to connect all these accounts to each other that you make sure that all these data flows are going quite smoothly. That's maybe a bit much to cover now in this one session, but then again, there are a lot of tutorials available on how to do this. And one of the sets of tutorials I definitely is worth mentioning are the tutorials from the Research Institute for Nature and Forest in Belgium, where they have a whole website where you can see how to connect your accounts with each other. And for example, here, if you look here in the list of tutorials available, there is a tutorial setting up the Zenodo GitHub integration, which we will show in a minute. So it will guide you step by step on how you connect your accounts together and how you then can make sure that you can do the publication to Zenodo in an automated way. And I really advise you to do this because GitHub, although it's already better than having your code simply on your computer, because when your computer crashes, your code is gone. Publishing from GitHub to Zenodo is that extra step that ensures that your code has a longer life and provides you with a unique DOI that you can refer to your code. In this section, actually, if you go to the tutorials again, it's not only setting up things, there are also a lot of tutorials on how you can use Git and GitHub and how you use certain GBIF R packages, how you do this. So if you are looking as a data source on how I need to code something, how I can set up something, this is definitely a good reference to have a look at. Okay, let's move to GitHub. Let's open one of the GitHub repositories, and I think we can we can go to the one that we have been using for the mini schools. This is how GitHub looks like. If you want to have more information on Git and GitHub, there is already a micro school organized by NITheCS that explains you how to use Git and how to use GitHub. Although it's actually quite natural, it does help to have some guidance on this, and it's definitely worth having a look at this micro school to become more familiar with Git and GitHub. What happens here is that you can save your code in GitHub, and you can actually add files into these repositories simply by using the user interface, but you can also do it automatically. And you see here that the demo practicals that we were using for our mini school are available in the GitHub repository. How now do we publish our data to this mini school? And this is another level of integration that we can do, is if we go and have a look at the demo Jupyter notebook that we had on Google Colab on building the data cubes. My apologies, my text is in Dutch, but it's just the principles. You see here, this is the code that I've been showing. In the meantime, I've also been updating a little bit and adding here and there something on the NetCDF format if you want to have a look into that. How do I now update this code on GitHub? Also here, there's a very easy integration. If you go to File, you can actually save a copy in GitHub. It will be in English. Since I connected my accounts to each other, you basically have to select the repository where you want to save it. In this case, it's the Mini-schools repository. I want to save it in the main. In the meantime, the name of this lecture changed a little bit, so I have to just check that I use the same name. Like this. And then I give it a little bit of information on why I'm updating this. So I just say updating to the latest version. And I make a link to Colab. So if I tick this box, you will see we will update it like this. It will make the copy. And then you will see that my data is updated according to the latest version. You will see that it's updated today, so just now. And you will have here the link to Colab. That allowed you guys in the previous lectures just to click the link and open this Jupyter Notebook in an own Colab environment. So very useful. And again, it gives you a persistent it gives you something in an open repository so people can go there and have a look at what you did. GitHub has a lot of additional options. You can open up to only certain people, open up to the whole public. These are all settings that you can make into this repositories, but it's worth having a look at it. And if you have more questions, please don't hesitate to ask. Okay, good. If I just now go to one of my own repositories as an example, what we can do is for example, here I have a repository which I linked up to a Zenodo repository. So actually every time you make a release of this one, it will update to Zenodo. If you want to know more on how to do this, this will bring us too far. Please have a look at the IMBO tutorials. They will guide you towards how to do it. Okay, good. One other thing I want to touch upon is now we gave you a bit of an overview very quickly on how you can publish your software and your data into open repositories, and we focused on one, but there are several ones. Another way of increasing the reuse of your data is basically make sure that the code that you write are according to certain style guides and according to the code, to the style guides of that specific language that you are using. And in the BCube project, which we already mentioned a few times in this presentation, we did develop certain guidelines on how you want to do your coding to make it sure that it's reusable and interoperable with other types of code. So if you go to the website on the documentation of BCubed, you will see here a link to a software development guide, which is actually a guide which helps you to write code that is easily understandable by others and is according to the style guides. So this is part of open science, making sure that you don't write your code in any random way. It might work, but it will not be readable by others. If you follow a few of these guides, if you follow these guidelines, you will ensure that your code is more readable by others. Okay, this was very quick, what I wanted to say today. I hope we provided you some links and some ideas on where to find what you want. If there are still open questions, please let me know. And in the meantime, I will give the word to Sandra.
Great, thanks, Maarten. I'm just going to share my screen quickly. All right, so to jump off from where Maarten left off, there's a lot of different ways that you can upload your data to these open portals. So we've stressed throughout this mini school the importance of open data, and in a community of specialists, if your data is not open, it's difficult to share your knowledge in this data-rich world we're in at the moment. And I think most of you probably would have noticed as well that when you're trying to learn a new language, a new programming language, or you're trying to figure out a new analysis, the sources that you use the most are those that have working examples. Many of us, I mean, me included, when I'm struggling with some code, if I can get a data source and an example of how they use that code and that data together, it helps me immensely to develop my own code with my own data. So I think that's definitely the value in it from a student point of view, but then obviously from collaborative research point of view, you can share your analysis and you can share a lot of the progress towards some research that you're working on in a bigger group. So I'm going to take you through now some examples of how you can access these data. So Maarten's slightly briefed on how you can upload your data, but once that data is uploaded, how do you actually access it? And if there is data there, how do you access it? So we're going to jump to, I'm going to post this in the chat quickly. I'm going to stop sharing this slide here and just give you the link to our GitHub site, which hopefully everyone should have at this point. All right, should be in the chat. And if I share my screen now so that you can all see that, if you click on that link I've just posted in the chat, you should come up with this page. So this is something that Maarten has already showed you, and where we've put the different codes that we've been working on over the last few weeks. So today we're going to be looking at an open science workbook. The other codes you'll see are here. So that's Prac 2 and that's Prac 3. Some of these other things are just logos. And the data that we've used in there is sitting in a data folder. But importantly, keep an eye on this GitHub site. So it's still a work in progress, and we're going to update our code as we go along and try to improve it as much as we can, and have a look at that B Cubed website as well. That second link, that first link that I put in there, that is also going to be a working document. So as we're developing new tutorials specifically on data cubes and biodiversity monitoring, have a look there and you'll see a lot of stuff popping up. So for today, we're going to work on Open Science Zenodo R. So if you click on that, it'll open up this, hopefully, there we go, it'll open up this Jupyter notebook. And again, you'll have this button here that says Open in Colab. Once you click on that, it's going to open it up in your Colab setting, and it will give it the same name, and you can then use the option to copy it to your drive so that you can have a local version. So if you want to keep this version intact and you want to start editing it, save a copy to your drive and then start working on it from there. All right, so there's a lot of text here just to give you a bit of a background on what Maarten's already said in his presentation, touching on the open science principles, and then giving you a list of the different open science tools for biodiversity monitoring, but also essentially any data. We're not going through all of them, but I think some of the biggest ones, GitHub as Maarten said, there's already been a micro school on that. Zenodo, which Maarten's taken you through briefly, the GBIF portal where you can access species occurrence data. It's another one which is also touched on and we've shown you throughout the last few weeks. And then there are a few others that you can have a look at, which also allow you to upload and download data. So today what we're going to do, the last 3 weeks, we've been using Python and Colab to start looking at data through GBIF. I thought today we could branch out and use R instead. So it works in a very similar way to Python. The only difference is that you'll see it's an RMD, but actually it's still a Jupyter Notebook file. So if you did have something set up in your R Markdown, you could upload it directly to the Colab and it will open in this format. I've created this in the Jupyter Notebook, but essentially it has the same setups as the R Markdown language. And then I've put these different tabs here so that you can jump quickly to different sections. I'm not going to spend too much time on some of the obvious things. I think most of you probably are using R over Python, so you shouldn't be too lost here. This section is installing the packages. Importantly, I put a few packages in here, and this will, the benefit of this over the second block here is that it will first look to see if you have it, and if you have it, it will skip the install. If you don't have it, it will start installing it. So we run that one. It might take a little bit of time for you if you haven't got any of these loaded. Specifically the SF package, which is for spatial features, and that one takes a little bit of time to run. So click on it and allow it to run. Once that's done, you'll have a number of different messages pop up for you underneath that window there. Mine doesn't because I've already had it installed. It's the same situation as with the Python options we sent you last week. When you close the session and you open it again, you have to reinstall some of these packages again. Okay, so once that's done and you've installed it, you load the libraries. So this should look exactly the same as what you would do on your own computers. The difference between this and what we did last week is that the runtime that it's using in the background is R. So when you set up a new Jupyter Notebook, you have to make sure that you set the runtime for the kernel to an R session and not a Python session. Click on it, it should install everything. And then what I tried to do here is give you an example exactly the same as what we did last week with the analysis. So I've taken the exact links that we used in our one last week, I've put in an R environment. So using GBIF data, this is the same function I had in Python last week. It looks for a zip URL, so a path, website path to a zip file that you've requested from GBIF. And this function essentially unpacks that zip file and reads it as a text file, and it will give you a message if there's a problem. So if you run it, you should hopefully get a little tick. It won't do anything yet because we haven't actually applied the script yet. We haven't actually applied that function. So here we assign the URL for the zip. So if you had a request from GBIF and they gave you this zip file to download, you can just replace it with that, put it in there, and it will apply the function we created. And I know these are the columns that I have in the table. It's the GBIF data, so it's got a lot of different columns, and I don't want all that information. So I've specifically selected columns that I want. If you've replaced this with something of your own and you want to keep those columns, then you don't use this part here. You can just comment it out and run it. In my case, I want that, so I'm going to run it. And hopefully it works. Let's have a look. There we go. So it's taken that from GBIF. it's read it in and it's selected only those columns that I've specifically asked for. And this is what it looks like. Similarly, you can do it with GitHub. So if there is a data set on GitHub that you want to access, in this case, we've got a CSV file that we've added onto our NITheCS GitHub site. That is the path to it. In that case, I don't need to create a function. It's already got an existing function called read delimited. So if I run that, it gives me that table. And if you'll remember from last week, this example had year, month combined into one column, and I want to separate it out. So I would use my R code now to separate those out into two separate columns. And I should now have, which I do, a year and a month column that separated those values into two. Again, as with anything in the coding world or in the analysis world, there's many ways to do the same thing. This was an example of the data I had in GBIF. Here is another set of data, but the one that came from the URL. So I took that zip and I unzipped it and I put it into my GitHub site and I brought that in as well. So it's just to show you, it does exactly the same thing. This is the raw data as it comes from the zip, and I want to select only those columns, and that's what I get. So it should be the same as the one further up. Yeah. All right, so now that we've got it into our notebook, now we can start doing things with it. And the first thing is to give this table the geometry of points. So we have the latitude and the longitude in this table, and we've got a number of other information in there, but we want to create a spatial feature out of this. So we've used this function, which is from the SF package, taken the table that we pulled in. It's told the function that this is where the longitude column is, this is where the latitude column is, and this code here is a projection that is a geographic projection, which is the most common. And over here, I want to create a boundary box. The reason I want to do this is because I need to create a grid later, so I want to see the full extent of where all my points are plotted so that I can make a grid over it. So you can take that from the existing spatial feature that you've just created, and you can have a look at them both. See, it has now created a simple feature collection. It's got 4 features. It's only 4 because I asked to show me 4. So there are a lot more in there. And now you'll see it's got this geometry type point, and it gives me the X min and the Y min and the X max and the Y max. So it's got a geometry associated with it too now. And this is the extent. Now I can create a grid over this. Now that I have the spatial location of my area of interest, because I know where all my points are lying, I can go and create a grid over those so that I can plot it. So this is the same as what we did last week when we wanted to calculate species richness over a certain area. You get your point records from GBIF as point locations of where someone has recorded it. You want to generalize it and look at how many are in a bigger area, in this case, a quarter degree square. So there's a nice function in the SF package that's make grid, and you can take the species points as your area of interest, set the cell size, and we want it to be a polygon feature. We can then convert that into a grid geometry and add that information to the species point. So at the end of the day, if we run this, you've got the same simple feature collection, which is the species point, but with an added grid ID associated with it. So if I add up everything and group it by that, it's going to be grouped by that grid that I've created. So here is where we do that. We've now got the species in grid, And that's the nice thing about the SF package, is that it treats everything. You can use the piping, so it treats it like a data frame. In the past with the SP, you had to use an at and a data and things like that. This is much quicker. So it's simply grouping it by that grid ID, and it's counting the number of distinct species that are in that grid. All right, and there we have it. So now we no longer have that long list of different species. We now have a grid ID and a new column that's called unique species with a count. So that's essentially species richness now put in those squares that you've created. Now, if we want to plot this, we can plot it immediately as it is using the point data, because it's still got a geometry, or we can link this information to the grid so that we can plot it as squares. So we can plot it as a grid. It's still going to be a spatial feature. It's not going to be a raster, but it will give you that it'll plot better with a grid environment as a polygon rather than a point. So that's what this is doing. It's just taking the grid that we created and it's linking the species count by that grid ID. So we now have a simple feature, but it's a polygon. It's no longer a point. If you don't believe me, if we plot that, you should, there we go. So now you get a map of, something is telling me if I'm a robot, but no. This is the map of South Africa with, in this case, remember it was all ducks and swans and geese and things. So this is the species richness of that across South Africa. You can also change the plotting environment. So it works a little bit differently because we're in Colab. So if you want to change the size of it, you need to run this function here to change the width and the height of it. You can then do the same thing that you would do in any ggplot, changing the title, the colors, etc. You can have a look at that. All right, and there you have it. So now we've got exactly the same map, but plotted in a different way with different colors and changed a few things. All right, so I'm running out of time a little bit, but I do want to show you Zenodo. So Maarten did take you through how to upload to Zenodo, and he gave you a brief rundown of the type of data that you can get there. And it's a really nice resource. And if you have a look there, as you said, there's stacks and stacks of data. So I had a quick look last night and found this Western Indian Ocean Coral Diversity Database. So this is the link here. And there's two different ways to bring this in. If you know the exact link, so if I was to follow that, where is it? I probably wanted to download it. So the issue is here is that I've specified that this is the download action. So if I go in here and I paste it like that, it says it doesn't find it. Let me try this. Okay, so that's the raw data. So by putting it in that format, it tells us that I can now download that file as is. But often you don't know what the files are in this Zenodo package. It often tells you that there's a zip file to be downloaded. So how do you do that? How do you take that zip file and start using it in your setup? So to do that, okay, so to do that, you can just copy it. I've told it where to go and I've given it a file name. And if I run that, you should hopefully get a little table. So if you know exactly where it is, you can copy that from the link. and here's the data that as it comes out. But as I said, sometimes you don't know what is in that record. So if you just knew where to find it, and hopefully this will work now if I just put this code in here. So that is an API record that tells you the metadata for this, this specific data set. And there are actually 2 files in this zip file. So for you to find that out, once you've pasted in the URL to that record and you run this function, it will give you a list of what files you've got in this record. And in this case, it's a zip file. So you've got 2 files here. You've got one that's a document and one that's a CSV. So I want to take the CSV. So I've told it in this setup here that it must go through this data set that I've found, and it must look for all the CSVs and return those to me so that I can see which one I want to add. Once I've found what it is, so it's given me these 2 options, I can then take that and use the download file to read it in. So this seems like a long way around, but you don't always know exactly what this URL is to download the data. But essentially it comes up with the same thing. You've got this table as it is. And then I had a bonus section at the bottom here, which would take you through using iNaturalist. iNaturalist data is in the GBIF environment, so essentially you can use GBIF and it would bring you the iNaturalist data. But I did want to show you that iNaturalist is another option where a lot of data is stored, and you can do a similar thing in R or in Python where you can read that data in, and works exactly the same way, where you can read the table, take the data, plot it, and have a look at different trends, etc., etc. So keep an eye on our GitHub site, and we'll update this tutorials and things for you. But in the meantime, are there any questions? I think you can just put your hand up and we can unmute you, or feel free to type in the chat.